So let's kind of play around with proving things in set theory. I mean, so far all we've pretty much done is like a lot of definitions. We haven't really proved very much. Proposition 3.6.4. Okay. So it says, well, so let A, B, and C be sets. And it says if A is a subset of B and B is a subset of C, then A is a subset of C. Okay. What I want to do here is go right to the formal definition of subset. So, right, so we're assuming, so since A is a subset of B, so we're assuming A is a subset of B, and B is a subset of C. We're trying to prove A is a subset of C, right? Does anyone remember the definition of this, the formal kind of logically implies definition of this? So this is from earlier today. Exactly. Thank you. Okay, so this is just the definition of subset. So my other premise is, so you should think of this as like a, two premises, A is a subset of B and B is a subset of C, and we're trying to reach the conclusion that A is a subset of C. So my other kind of assumption here is that B is a subset of C, which tells me something very similar. So if X is in B, that logically implies X is in C. Does anyone remember the chain rule? Can you see a chain rule kind of forming here? Or maybe it's already formed, I guess, right? So remember, the logically implies thing is the same as like an implication, except it's like an even stronger implication. It's like it's a tautology, but really inside of here is an implication, right? And this is an implication. And if I have something implies something, and then I have the same thing implies something else, then I can chain these together. So by the chain rule, X in A logically implies X is in C. But then I'm done because this is the definition of A being a subset of C. So A is a subset of C. And that completes the proof. Okay, so this is kind of like a chain rule for sets, although, yeah, I would be careful with that. Like, I mean, in some sense, subset is kind of like an implication, but for sets. But I wouldn't think of it too much like that because, for example, A subset B, this is not a set, right? So, yeah, it's whereas P implies Q is a statement if P and Q are statements. But in some sense, this is kind of a chain rule. If A is a subset of B, B is a subset of C, then you can kind of put that together and say A is a subset of C. Okay. Any questions about that? Okay, so next time we're just going to continue doing more and more proofs using these definitions. So I really suggest being pretty confident with these definitions. Okay, so let's get started. Okay, more stuff about sets. Okay, so yeah, basically we're gonna do a few proofs involving sets, and then we're going to yeah, maybe introduce one more concept. Okay, so this is one of the propositions from the course notes. It's 3.6.5. It says, basically, if you have two sets, then A equals B, like, is the same thing as, so in other words, A being equal to B is logically equivalent to A being a subset of B and B being a subset of A. So in symbols, like, in other words, this is saying, so when I say an if and only if, what we're really saying is that this statement is logically equivalent to A subset B and B subset A. Okay, but I mean, normally you'll see this written in words, right, rather than in symbols, but yeah. Okay. So let's try to prove this. So what I'm going to, so how do you prove an if and only if? I mean, so what we need to do, we need to show that this is equivalent to this. So what we can do is we can start by saying, okay, assume that this side is true. So assume A is equal to B. And then from that assumption, we derive that A is a subset of B and B is a subset of A. And then that proves one direction, right? And then for the other direction, you assume these things and you derive this, right? So there's sort of two directions we have to prove. So first, so the way you might see these things written is like, starting with this. So saying, this is trying to communicate, first we're going to prove this direction. So actually, and this might not be, of course, like I said, you're probably not going to see these things written in symbols, but to say that we're proving this direction means we're proving that A equals B implies, A subset B, B subset A, right? So you should think of this if and only if as being this kind of double arrow thing. And we're proving this direction. So in other words, we assume that A is equal to B. Does anyone remember what it means for two sets to be equal? Yep. Yeah, that's a good kind of way of saying it kind of in normal English. For the purposes of this, it's going to be useful to write it in symbols, but yeah, it means that the elements are the same. So kind of symbolically, what it means is that X is in A is logically equivalent to X being in B. But yes, in normal human language, it means they have the same elements. Okay. Does anyone remember what subset means, actually, in symbols? Just kind of put this on the side so we know what we're trying to do. Does anyone remember this, the definition of subset? Yeah? Exactly. So it's kind of like one half of this thing, so it's just like X being in A implies X is in B. So basically what we're trying to do is, we want to show that A is a subset of B and B is a subset of A. It becomes kind of clear that what we're trying to do is break this thing up into two parts. And remember, remember this thing about how the double arrow is equal to two single arrows? So that's all that we're going to do here. So this implies, so double arrow is the same as these two single arrows, right? In other words, an equivalence is the same as two implications. Okay, here what we're using really is this thing that P if and only if Q is the same as P implies Q and Q implies P. Now, yes, these are thin arrows and these are thick arrows. right? But the thick arrows are just a special type of the thin arrows, right? They're just, yeah, these are really the same thing, except this is saying something special, that this is a tautology, but really they should behave, they have the same properties as these thin arrows, right? So I can break this up into two single arrows. This one tells me that, the first one tells me that A is a subset of B, and the second one tells me that B is a subset of A. So this does prove that, so we started with the assumption A equals B, and we derived A is a subset of B and B is a subset of A, right? Okay, so what do I have to do to finish? So the proof's not over, right? Because, yeah, we're trying to prove an if and only if here. And I've proven that this side implies this side. So I've got to do the whole thing backwards, right? So we need to assume this A is a subset of B, B is a subset of A, and derive A equals B. But, I mean, if you think about this, like, all we have to do is just do this proof backwards, right? All of these steps were reversible. So if I say A is a subset of B and B is a subset of A, that gives me this line, right? So this implies this, which implies that, and I can basically just do the whole thing backwards. And sometimes that's going to be the case, right? Sometimes when you're trying to prove an if and only if statement, it will be the case that, you just do it in one direction and the other direction is just completely reversing those steps. Now, I'm not going to guarantee that, though. So there's a lot of cases where one direction can be proved very easily and the other direction is a totally different, uses a totally different idea. But in this case, it's quite simple, right? So all we have to do to prove the other direction is just reverse this proof. Okay, so, okay. Well, maybe I'll cover that up and we can do it again. But yeah, so maybe I'll do this one kind of quickly. So for this direction, so we want to assume this stuff and prove this. So we assume A is a subset of B, and B is a subset of A. So by definition of subset, this, so I'm maybe writing more words in this direction, but you don't really necessarily need to. So this tells us that, so the A subset B tells us that X in A logically implies X in B. That's just the definition. And you have the other direction as well. And again, two single arrows with an and between them gives you a double arrow. So therefore, X in A is logically equivalent to X in B. And so A is equal to B. Okay. Any questions about any of this? So this is something to watch out for. If you're asked to prove an if and only if, you have to prove both directions. But sometimes, once you've done one direction, you can just look at your proof and kind of notice that everything can be reversed. And then you just kind of do it backwards. And it doesn't always work, but in this case, it works. Okay. Like, the important thing here is every step we use the logical equivalence. So that makes it reversible. Okay, so let's do another set theory proof using a slightly different approach. So actually, this proposition here, I would say this is quite an important one to remember. So remembering that the actual statement of this, because this kind of describes the way that I would say most mathematicians, if they're proving one set equals another set, most cases you want to use this proposition to prove that. So the sort of method, so one method of showing that a set equals another set of showing a set A equals a set B is to show that A is a subset of B and B is a subset of A. Actually, on your brand new worksheet number 4, which I guess you guys received last night, there's a question which says, like, prove something about sets by starting with the words, let X be an element of something. That's how this kind of proof would work, right? If I want to show A is equal to B by showing this and this, the first line of the proof will say, well, let X be an element of A, right? And then you want to derive that it's an element of B. And then you'll start, let X be an element of B, and you'll derive that it's an element of A. So actually, there's a question on your assignment which is asking you to prove things using kind of this method. So maybe I'll give you an example of that. And basically by following similar steps, you should be able to do the assignment question. Let's prove De Morgan's law for sets. But can anyone remind me what it is? Okay, of course there's 2 De Morgan's laws, but what's one of them? Yeah.
The negation of Q and P, logical equivalent to negation of Q or the negation.
Yeah, so that's De Morgan for statements, which is, it's basically the same as for sets. But for sets, there's it's the same thing, but you just replace these ands and ors with intersections and unions, and negation becomes complement, right? So you're totally right that this is De Morgan's law, right? So negation of P and Q is the same as, or logically equivalent to, negation of P or negation of Q. The set version of that is the complement of A intersect B is equal, so the equivalence becomes equal A complement union B complement, right? You should think of the complements as being the negations. The and is the same as the intersection. The or is the same as the union, right? Okay, this is something to memorize, right? We talked about this last time, but yeah. Of course, complement only makes sense if there's some sort of universe that these sets belong to, right? So always when we write complement, we kind of assume that these sets are belonging to some universe, if that makes sense. Okay. Any questions about this? Do we remember these definitions? Maybe I should quickly write them. So A union B is the set of all X such that X is in A or X is in B. So just to remind you quickly what these things mean, set of all X such that X is in A and X is in B. You should remember this because this looks like an and symbol, except it's curvier, and this says and. This looks like or, that's or. And the complement is the set of all X in U, where U is the universe, such that X is not in A. Okay. And this is like a negation, right? X is not in A. Okay. Okay, so I want to prove De Morgan using this idea of showing, so I want to show two sets are equal. So therefore I want to show that this one's a subset of this one, and that this one's a subset of that one, and then I'll be done. So we want to show that A union B complement is a subset of A complement intersect B complement, and vice versa, that this one's a subset of the other one. Okay. You don't really need this line, but I'm just trying to explain what we're trying to do. And if we do that, then by this previous proposition, we will have shown that they're equal. Okay. I know this is the part that kind of connects to your assignment, your new assignment. So we start the proof by saying, let X be in this set. Okay, so X, we're just assuming X is any element of this set. And if we can show that any element of this set is also an element of A complement intersect B complement, then we will have demonstrated that this is a subset of that. So we want to derive that X is in here. Okay, is that clear? Or any questions about any of this? Okay, maybe I'll write that to make it kind of clear, but you don't necessarily have to write this all out. But we want to show that X is in A complement intersect B complement, because that will demonstrate this subset relation here. Okay. What does this mean? I mean, in words, that X is in the complement of A union B. Yep.
Not A or B.
Exactly. Yeah. Yeah. So let's kind of break that into two steps, but that's exactly the point here. So, okay, if X is in the complement, this tells us that X is not in A union B. Right? Being in the complement is the same as not being in the set. I'm not sure if that helps me, really. Well, okay, I can say then that X is not in A, because if X was in A, it would be in the union of A and B, because the union contains everything in A. And similarly, X is not in B, because otherwise X would be in A union B. What's next? Any thoughts? Oh, just stretching. Well, okay. What does this? Suppose I try to do something similar to this. So I said here, I was like, X is in here. That means it's not in the union. What if you try to do that backwards here? So X is not in here. Yeah.
Yeah, so
Exactly, yeah. And so if we kind of reverse that, so if X is not in A, it means that X is in A complement. And if X is not in B, it means that X is in B complement. Now we've got an and here. So it's like X is here and X is here. And that's the definition of X being in the intersection. So, right? So something is in the intersection of two sets if it's in both of them. So therefore, X is in A complement intersect B complement. And so A union B complement is, in fact, a subset of A complement intersect B complement. Because what we've demonstrated is that X being in here, if we assume X is here in A union B complement, we can deduce that X is here in A complement intersect B complement. And that's the definition of being a subset, right? That this logically implies this. Now we have to prove the other direction, right? But is this direction okay? This is a very standard way of proving two sets are the same, right? You start with proving that one's a subset of the other, and then vice versa. So how should I start the next part of the proof? Any thoughts? Exactly. Yep, I like that. So, right, because what's left to prove? Okay, we already did this. That's like a check mark. We've done that. We haven't done this. And so we're going to do this in exactly the same way. So we let x be in A complement intersect B complement. Now, if you think about it, we can pretty much, again, like, we can pretty much just reverse this whole process, right? So if x is in here, then that means this, right? So therefore, x is in A complement, and x is in B complement. We can reverse this, right? Because being in A complement is the same as not being in A, and not being in B, being in B complement is the same as not being in B. So that's the same as this. Okay, and if x is not in A and x is not in B, then x can't be in the union of A and B, because the union is the set of all things that are in A or in B. So this is saying, so if I have the statement, like if you think of the statement, or so A union B. So remember this set, what this set builder notation means. It's a set of all x such that x is in A or x is in B. So it's the set of all x such that this statement is true, x being in B, A, or this statement is true. So if both of these statements are false, then x is not in the union. Here, we've proven that both of those statements are false, right? X is not in A and x is not in B. So x is not in the union of A and B. I guess by definition of union, right? Kind of, because x is an element for which both of these things are false, so therefore it's not in that set. And so x is in the complement of A union B, and therefore A complement intersect B complement is a subset of A union B complement, and that completes the proof. By the way, you can kind of see I'm writing, I don't know, so and therefore in sort of random places. Yeah, this doesn't matter so much. I mean, you don't have to remember where to write therefore. So here I wrote therefore in the second last line. It doesn't. These things don't matter. Well, so this whole proof could have been done just by taking the union and kind of expressing it with ands and ors and nots, and then using De Morgan for logical connectives, right? So that is a totally valid way to do it. There's no good, I don't have like an answer to why we didn't do that. Like, you can also do that. There's more than one way to prove these things. Yeah. Yeah, actually, in this case, I mean, it would have been easier to do it that way. I can show that, like, so let's see another proof. Because that is actually good to think about it that way too. So, in fact, so in the notes, I think they prove it the way I just did right now. But when I was reading the notes, I also had the same question as you. We already know De Morgan works for logic. Why wouldn't we just use that? It's a very good question. So let's do another proof of De Morgan. Actually, well, let's prove the other De Morgan, right? There's two different De Morgan's laws, right? So let's do the one where it's like you negate. Wait, which one did we already do? Yeah, if I take this. Okay, so it's kind of not a second proof. It's kind of proof of the other De Morgan. But so we want to show this. Okay. And yeah, you totally can do this just using laws of logic. So I can just write A intersect B complement is the same as the set of all x such that, well, such that x isn't in the intersection, right? Because it's the complement of the intersection. I'm going to write that in logic. So the negation of, well, x in A and x in B. So this, you should always read this as x such that this statement is true. So this is x, all x such that it's not the negation, so it's not true that x is in A and x is in B, right? Is it clear that this is equal to this set? Because the intersection would be x is in A and x is in B. Now I take the complement that negates that. And by laws of, by De Morgan for logic, this is the set of all x such that, well, negation x in A, right? Because when we have two statements and you have a, it switches the ands to an or. And it negates the things inside. So this is by De Morgan for statements. And now we're done. Because this is the definition of being in the complement of A or the complement of B, which is the union of the complement of A and the complement of B. Okay. So that's a better proof, to be honest. But I wanted to demonstrate this whole thing about, proving that something's a subset of something and vice versa, because you have to do that on your homework. So, okay. Any questions about this? So actually, all these laws of set theory can be proven by just writing the set builder notation and then using a law of logic and then converting it back to sets at the end. So maybe I should say all laws of set theory can be proved similarly. By deriving it from the corresponding law of logic. Okay, but yeah, like I said, you do have to get practice with this whole, this subset that thing. So let's do another example, which maybe doesn't easily follow from laws of set theory. Maybe it does, I don't know. So I don't know, I'll call this a proposition. So let A and B be sets. So what I want to prove is that if A union B is B, so it's equal to B, then A intersect B is equal to A. Seems a bit weird, but that's what we want to prove. Okay, so this is an if something, then something statement. So what we want to do is assume the premise here, like we assume that A union B is equal to B, and we want to derive that A intersect B is equal to A. So let's assume A union B is equal to B. Okay, and yeah, so I'm kind of, again, going to write some extra detail, but we want to show that A intersect B is equal to A. Okay, so my suggestion here is, prove that this is a subset of this, and this is a subset of this, right? Okay, so in other words, so we show, so this is all kind of, I think this is all really extra detail, but that you don't necessarily always have to write, but if it helps you, then you should write it, right? And that A is a subset of A intersect B. Okay. Okay, how should I start? I mean, it looks like I've already started, but I've just sort of laid out what we're going to do, but I haven't really proven it. I haven't done anything really. So how should I start? Okay, let's start. Well, let's start by proving this one, right? So a nice rule of thumb, you can pretty much always start these proofs by saying let x be in something. So I guess if I want to prove this one, I want to let x be here and prove that it's here. So let x be in A intersect B. This subset relation is really easy to prove, right? Can anyone see? It's like this tells me that x is in A and it's in B, so like I'm already done, right? So this tells me x is in A and x is in B, but I don't even really care that x is in B. So like in particular, x is in A, right? I mean, I don't really care that it's in B. And so, yeah, A intersect B is a subset of A. And actually, I didn't even use my assumption, right? I have this assumption, I didn't use it. But it doesn't matter, right? I still proved it. But we have to prove the other direction now. So how should I start the proof of the other direction? When I say the other direction, I mean this thing. Yeah, totally, yeah. So let x be an element of A. And we want to prove that it's in here. Now, okay, we've already got half of that, right? Because, right, we want to prove it's in A intersect B, which is the same as saying it has to be in A and in B. So what we really, our whole goal in life right now, we don't care. We've already got that it's in A, that's fine. We want to prove that it's in B. That's our whole kind of goal here. How the heck are we going to do that? Yeah. Yeah, and I think I would suggest always remembering this. Like, we haven't used this yet at all, so we should use this. So here's one thing I can say. If x is in A, and this is kind of trivial, but then x is in A or x is in B. Well, this seems like a stupid thing to say because it's in A. Why would I care? Yes, of course it is in A or B, but because it's in A. But that tells me that x is in A union B. A union B is B by the assumption. So by the assumption, A union B is B, it's equal to B, so x is in B. Therefore, x is in A and x is in B, so x is in A intersect B, and therefore A is a subset of A intersect B. Okay, that part I went a bit quick, but so this is the general method. You want to prove two things are equal, show that one is a subset of the other, and vice versa. Okay. Any questions about any of these steps or anything at this point? Okay. Yeah, so my suggestions, start your proofs with let x be somewhere. Another suggestion is use your assumptions because otherwise you're probably not going to get anywhere. Okay, so I want to do one more proof, a set theory proof using the laws of set theory. Okay, so let's do a proof using the laws of set theory. But first, let's remember, sort of, just quickly, refresh what they are. So I'm not going to write them all out, but I'll just say all the laws of set theory are very similar to the laws of logic, except that or in logic, becomes union and becomes, does anyone remember the name for this? What is and? Yeah? Exactly, yeah. Make sure to have these names. We did the Jeopardy ICA last time. Most people remember that this is union. A few people did say intersection or even other things. So remember, these are union and intersection. Negation. Well, what does negation become when we do laws of set theory? Yeah, exactly. Yeah, so if we had like a not P for like a statement, it becomes like A complement, where A is a set. Contradiction becomes empty set. Tautology becomes, I'll just write U, where U is like the universe, right? So often when we're doing laws of set theory, we might have like some universe in mind, and tautology becomes the universe. Okay, so let's do a proof using laws of set theory, because I don't think we've done one of those yet. So this is proposition 3.11.5. So fortunately, I don't think you had to do one of these on your assignment, right? You had to do a different type of set theory proof. But in the future, you might be asked to do a proof using laws of set theory. That could happen. So we need to know how to do that. So it says let A and B be sets. So then A with this little plus thing, B is equal to A union B minus A intersect B. Anyone remember what the little plus is called? So what is the name of this? Yeah, exactly. Yeah, symmetric difference. I know, yeah, this was a long time ago now when we defined this, and we haven't used it very much, but you have to remember this definition. Also, what was our definition of symmetric difference? Actually, maybe I'll just even, that can be my first line of the proof. So I want to prove this using laws of set theory. But as a first step, can anyone remember what we actually defined this to be? Yeah? Exactly, yeah. Good. Okay. This is just the definition. The original definition of the symmetric difference is that, right? By the way, if you look at a kind of Venn diagram, the symmetric difference is everything which is in A or B, but not, in there. So it's A minus B plus union B minus A, but not the. So actually, if you look at the picture, it's kind of clear that this would be the same thing as taking the union and subtracting the intersection. But I should say, drawing the picture is not really a proof. It kind of tells you that this thing might be true, right? But it's not quite a proof. So we have to still prove it. So yeah, so the stuff I've scribbled in, that's the symmetric difference. Okay. So let's continue with this proof. So here's something I want to notice, that if I take A minus B, well, I mean, this is all the things which are x such that x is in A and x is not in B by definition. But if you think about it, you know, that's the same thing as A intersect B complement. So this is by definition of A minus B. And to say that this is equal to that, this is just by definition of intersection and definition of B complement, right? I mean, to be in, so to not, x not in B means x is in B complement. X is in A and x is in B complement. Well, if you're in two different sets, that's the same as being in the intersection. Okay, so I'm just trying to, so I'm taking this definition, or this thing here, and I want to replace this with something that's a little bit better for using the laws of logic. We don't have a law of logic, or sorry, laws of set theory. We don't have a law of set theory that involves like A minus B, right? But we have laws of set theory that involve A intersection B complement or things like that. So I just want to make a little substitution. So similarly, we have that B minus A is B intersection A complement. So we can write, well, so maybe I'll just rewrite that first step. So that's the same as A intersection B complement union B intersection A complement. Okay. So this step was just to make it a little bit better for using laws of logic. But is that okay? Okay, can anyone see, I don't know, does anyone have a feeling of like, so I want to use laws of logic, like which one should I use, or any, I mean, there might even be multiple options, I'm not sure, but can anyone see any option? Yeah? Yeah, totally. So, right, because you can see that this is some kind of set here. It's a complicated set because it involves intersections and complements, but anyway, this is some kind of set, union, an intersection of sets, right? So we can kind of pull that thing inside, right? So remember our distributive law says if you have something of the form x union y intersect z, you can write that as x union y intersect, am I doing this right? Yeah, x union z. This is just the distributive law. And if I think of this as being my x, that being my y, and that being my z, we can distribute it. Is that clear? I think the weirdest thing about this is that I'm just going to treat this as like, you know, just one set kind of thing, right? Which it is. It is a set. So I can distribute it. It becomes a bit ugly now, but, right, so I want y intersect b complement, union b, and this whole thing intersects A intersect B complement, union A complement. Did I do that right? This does have this form, right? It's something union, the first thing that was in this bracket, the same thing union, or the second thing in that bracket with an intersection between them. So this is by distributivity. Okay. So yeah, you should probably give your reasons for these steps, just like in a law of logic proof. Okay. Is anyone confused by that? It's like the notation gets ugly, but okay, does anyone have any idea what to do next? Yeah, you can do more distributivity, right? So like maybe inside of these things, right? Is that the, you can, yeah, so if you look here, for example, we've got like a distributivity thing we can do, right? We can bring that one inside those ones. And you've also got another distributivity thing you can do here. So this is going to be equal to, okay, A union B. So I'm distributing the B inside of that intersection B union B complement. And then I do the other side, A union A complement intersect B complement union A complement. Okay. And my reason is distributivity. Maybe I'll just, for clarity, I'll write times 2 because I actually used it twice. Okay. Does anyone notice anything here? Yeah. Oh, it's equal to what? Yeah, totally. I mean, so maybe just to be nitpicky and a little bit careful, I wouldn't call it a tautology, but it's this kind of the set theory equivalent of a tautology. But it equals the universe, right? But whatever, that's the same. Yeah, tautology is like the right idea, right? And this is kind of also a tautology, or really it's the universe, right? This is kind of like our basic tautology, P or not P, This is like the things that are in A and union the things that are not in A. So that's everything. That's the whole universe. So I can write that as this. Because, I mean, I don't know if what I should write as the reason, but I mean, A union A complement is the universe, and B. I guess you could say like known, I don't know. You can't really say known tautology because it's not a tautology, it's not logic anymore, but anyway. Does anyone know what to do now? Yeah, exactly, yeah. And this actually has a name, but yeah, exactly, that's the concept, right? If you take any set and then you intersect it with the whole universe, it just gives you the set that you have, right? So, because if you say all the things that are in A union B or the universe, or sorry, and the universe, that's all the things in A union B, because, yeah. So this actually has a name, but this is totally the right concept here. So we can do the same thing on this side. And this is actually one of these rules called identity. So the identity law. So identity says that like if I have X intersection U is X, for any set X. That's what the identity, There's another identity involving the empty set as well. But yeah. Okay, we're not done. We have to still do some more stuff, right? This isn't quite what we wanted. It's looking kind of good because we've got A union B, but it's supposed to be A union B minus A intersect B, and it's not that, right? It's maybe not clear what to do next, but yeah. Yeah. It's kind of hard to explain in words, but like using De Morgan's law, you can kind of pull out a C here, right? Because, okay, one thing you should always keep in mind here, we know where we're trying to get to, so let's try to get there, right? So I know I want to be taking like the set difference with A intersect B, which is the same as taking the intersection with the complement of that set. So let me just write this and then explain why it's true. So this is true. Well, actually, it's kind of clear why it's true. It's just De Morgan's, right? If I take B intersect A and you complement it, what always happens is the complement goes inside and it changes the intersection to a union, which is exactly what would happen, to get to there, right? So this is by De Morgan. Okay. Is that step clear? I mean, it kind of seems like I'm cheating because I just wrote down what I wanted, but it is justified that this is equal to that because that's how De Morgan works. It's kind of backwards De Morgan, right? And then I can just write that this is A union B minus A intersect B, because we already proved this thing before, that if I take a set intersect with the complement of something, it's the same as taking the set minus that thing. This is of the form a set intersect with a complement, so it's the same as that minus that. Okay. Any questions about that? Okay, so if you've done like a million laws of logic proofs, then this is the same thing. You just change the symbols, basically. You make them curvier, and you write C's instead of little weird line things. Okay, or hockey sticks.